Hello, and welcome to Lesson 15. So today we're going to be talking about surface area. So let's go ahead and get started. So in previous lessons, we've learned how to find the area of different shapes. In fact, all three of these shapes we've discussed in previous lessons. So just as a quick review, how would I find the area of a circle? What is the formula for it? I'll give you a second to say it out loud. The formula is area is equal to pi r squared, right? And how about the area of a triangle? What's the formula for that? Area equals 1/2 times the base times the height. And the area for a rectangle is area is equal to length times width. All right? So these three shapes we've been dealing a lot with, and we've been dealing with sometimes we'll even deal with a shape that's a combination of these shapes. But today we are going to take a step forward here, and we're going to be talking about a different kind of shape. We will be leaving these shapes behind. These shapes are all two-dimensional shapes, which means that they are flat. All of the lines that make up these shapes, they're all composed of just movements either from the left to the right or up and down the page. So everything is either up and down or left and right. Those are the only two directions we can go when we're creating these shapes. There is no depth to them, right? There is no depth. So this shape, for instance, this triangle, it doesn't go back into the page. It doesn't pop out of the page. It is flat on the page. So today we're going to be going into three-dimensional shapes. All right, so a shape that looks like this. Now you might argue that this shape is also flat. It's certainly not popping out of the page. And you'd be right. I obviously can't make it pop out of the page, but I can trick your mind a little bit. And by the way that I've drawn this, it can appear that this shape is coming out of the page or is going into the page. All right, essentially, I've given it the illusion of depth. All right, and that's what three-dimensional drawings are all about. Three-dimensional shapes, they have depth. We don't just have left to right movement and up and down movement, but we've also got depth, going inwards movement and coming out movement. All right, so this is going to be the topic for today. Three-dimensional shapes and how we can find the surface area for three-dimensional shapes. So first, let's just get a couple of terms out of the way when we're talking about three-dimensional shapes. And the first thing is to just categorize them. So all of these three-dimensional shapes that you see on the screen, these would all be considered geometric solids. That's the name we give to these. So in algebra, whenever you hear those words, geometric solid, just know that you are dealing with a three-dimensional shape. Geometric solid. Oops, solid. All right, so maybe I will just circle all of these. So all of these can be enclosed in a group called the geometric solid group. All right, now we can subdivide that group into several other categories, and they are kind of important, so we'll just briefly run through them. One category that you may run across is something that's called a right solid. And we've talked about right triangles before. Remember, they have 90 degrees in them. The same thing applies for geometric solids. If the shape has right angles at the base, so if we have this rectangular box shape here, the base is the bottom of the shape. So the base would be this part right here. Okay? And if the lines extending up from the base are at a right angle to the base, so if you look at this, this forms a right angle, right? This one also forms a right angle. All of them, in fact, form right angles with the base. And if that is the case, then we give this a specific name. We call this a right solid. A right solid. Okay? Now, the reason that's kind of important is because if the shape is a right solid, what that indicates is that the bottom of the shape is going to be the same shape as the top of the shape. The bottom and the lid will be exactly the same in dimension and in shape. They're both rectangles and they will have the same size. All right? And that'll always be the case for right solids. Now this shape over here is clearly not a right solid. Here we have our base right here, right? If you're looking at this from the right perspective. And do the sides come up at right angles to the base? No, they don't, right? This is going to be at a slant or an angle that's not 90 degrees, right? And this one is too. So clearly the sides do not come up at right angles to the base, which indicates that it is not a right solid. And it also shows that the top is not going to have the same dimensions and shape as the bottom. In fact, you could argue this one doesn't really have a top. It all comes to a point. There isn't really a lid to this one. All right? So the key thing to remember is if all of the angles are right angles at the base, you know the top and bottom are exactly the same size and shape. All right? So let's take a look at this one here. This one is, you could say, it does have kind of right angles, right? If you look at the base, these lines are coming straight up from the sides, right? But there's one key difference between this shape and this shape. What might that be? Can you think of it? Well, if you look at the base on this one, it's composed of curved lines. This one is not. All right? So a right solid, we already said that a right solid needs 90 degrees. I'm going to add another note to that. So it needs 90-degree angles. It also needs to have a base made up of line segments. Excuse my slanted writing here. Base made up of line segments. Maybe I'll put in parentheses here. Essentially what that means is that the base is a polygon. All right? So this base certainly has line segments. It is a polygon. This one over here, though, this is not a polygon. The base has curves to it. So not a polygon. So we have to give this another name. So instead of calling it a right solid, we're going to call it a right prism. So this is an example of a right prism. All right, so keep those two in mind. You've got your right solid and you've got your right prism. One's circular, one's made up of line segments, polygons, as their bases. And then you've got this shape here, which is neither one. It's not a right solid, and it's not a right prism, but it is a geometric solid. Okay? Very good. So now that we have that cleared up, let's move on, and let's talk about surface area in particular. What is surface area? Well, it's exactly what it sounds like. It's the area of the surface. So one way to think of it is if you have a three-dimensional shape, such as this box here, and you're trying to wrap it with wrapping paper. Maybe it's a gift and you want to gift wrap it. All right. How much wrapping paper do you need to cover all the sides of this box? That is the question. To answer that, you would have to calculate the surface area of this box. All right. All that really means is we take up all the areas of all the different sides and we add them all together. And that's what this definition is saying. The surface area equals the sum of the areas of all the sides of a shape. So it's actually really straightforward, in particular for rectangular boxes like this. So how would I find the surface area for this shape? Let's do it. Well, you might start by just counting up how many sides you have. All right, you have the bottom, you have the top, you have the back and the front, and you have the two sides. So you have 6 sides all together for this shape. So maybe just throw that up in the corner. We need 6 different sides here, 6 different areas. All right, now we might note that this particular shape is in fact a right solid, right? We have these 90-degree angles. And that's important because what that means is that the area of this base, and we'll call this side right here the base, the area of this bottom, the base, is going to be the same as the area of the top. So if we figure out one, we can also know the other. It's kind of a shortcut. All right, so let's find the area of this base. Well, the base is simply a rectangle. And how do we find the area of a rectangle? What's the formula? Length times width. So in this case, our length is 6, Our width is 3, so we have 6 times 3, which is going to be 18, and we're going to say this is inches. So 18 square inches is going to be the area of the base. But that also means that the lid, the top, also has an area of 18 inches squared. So over here, we're going to have our little tally here. We have our 18 inches squared for the top, another 18 inches squared for the bottom. So we've got those two sides figured out. So let's move on now to some more sides. Let's take this side right here. Okay. And in order to find the area of that, we need to know the dimensions for it. So what's the dimensions, or the dimension of this side of the shape? Can you figure that out? Well, it's going to be 5, right? It's going to be 5. So if it's 5 on there, and then what's the dimensions of this width, we'll call it, along the bottom? Well, it's going to be the same as this width, so it's going to be a 3. So we end up with a 5 on the side, 3, if you can see that, on the bottom. Maybe I'll put it up here, 3 up here. All right, so what would we have for the area for that side? Well, it's pretty straightforward. Area equals length times width, 3 times 5. Right? So it's going to be 15 inches squared. That's the left-hand side of this box, so we'll throw him over here. Now, if you could kind of picture, I don't know if I dare do this, flipping this box onto its side. If I were to just go like this, I know my writing's all going goofy, but you can kind of see I'm flipping it on its side. And that orange side, if the orange were to travel with my box, the orange would now be on the bottom, and all the lines coming off of that orange would be right angles. So it would still be a right solid, which means the bottom that you see now would have the same area as the top. And the bottom is the orange, even though my orange lines aren't in place. So the top is going to be the same as the orange, okay? The orange bottom. So if I flip this back into position, all I really just said was that we can, by knowing this side, we also have found this side, is all I'm saying. We're treating this first side as the base. These are right angles coming off of that side, so that means the opposite side will be the same shape and size. All right, so because we found this to be 15, then this right-hand side of the box is also going to be 15. All right, same thing could be said for the front and the back. Again, we're all at right angles, so the front and the back are going to be the same size as well. So let's try to figure out the area for the front. And I know my picture is getting a little bit messy here, but essentially we're figuring out the area for this front here. All right, so what's the area of the front? Well, we have our length, which is 6, and our height, or our width of this box, this face, which is 5. So we have length times width is going to be equal to 5 times 6, which is going to be equal to 30. And again, we'll call it inches squared. So the front is going to be 30, which then means the back, way back here, is also going to be 30. And now we have 2, 4, 6 sides that we've calculated. So we've covered all of the sides of this shape. The last step is simply to add all of them. So if we have 8 and 8 is 16, plus another 10 is 26. And then we have 2, 4, 6, and 6 is 12. So we have 126 inches squared. All right, so we would need 126 square inches of wrapping paper to completely cover this whole box. And that's without any overlaps, by the way. It would have to be perfect. But that's how much we would need. All right, so hopefully that makes sense. That pretty much sums up the intuitive part of what surface area is. You're just finding the area of all the sides and summing them together. But now let's get a little bit trickier here. Let's go to a different shape. So for this particular shape, we're talking about a right prism in this case. If I asked you to find the surface area, it may not appear to be quite as intuitive as the last one was. We can still use some formulas. and we can still use some observations to help us, but there is a little bit of a trick to this. So let's take a look at this shape. And actually, if you want to pause the video and try this one on your own, go for it. See if you can get it right, and then we'll do it together. All right, so let's proceed. First off, we have our sides. How many sides do we have? Well, we have this bottom right here, and we have this top. Now, are they going to be the same size? That might be a good question to start with. Are they going to be the same size? They look like they're the same size. The answer is yes, they will be the same size so long as these are right angles from the side to the base. Then we'd have that right prism, essentially, going on. All right? And then the bottom and the top would have to be the same. So I'm going to tell you that they are at right angles. So yes, we can assume the bottom and the top are exactly the same. So how would we find the area of those two sides? Let's just start with that. So we know how to find the area of the circle. The area of a circle is pi r squared. Well, that's easy enough. We know what r is. It's 3, and again, we'll call it inches. So it's pi 3 squared, which is 9 pi. 9 times pi. I'm going to leave it at that. I won't multiply that all the way out. I'll just leave it at 9 pi. All right? So we have 9 pi. I should probably put square inches here. That is the area of this top, but that's also the area of the bottom. So if we're trying to find the surface area of this whole shape, we're going to say over here on our left-hand side where we kind of keep our tally here, we have 9 pi for the top. We also have 9 pi for the bottom. Okay? Now, the tricky part here is finding the area of kind of this side. And if you picture this shape as kind of a can, this side is curved. So it's not a rectangle per se, at least not the way it's sitting right now. It's a curved side, which makes it tricky. How could you find the area of that side? Well, to do so, I'm going to back some of these out. We're going to have to use our imaginations here a little bit. What we're going to do is pretend this is a can, and we're going to cut the can. We're going to slit it right up the middle, just like that. All right? I guess we'll come all the way down, just like that. We cut it right up the middle of the front. All right, and then what could we do? We could then take those sides, if we've removed the top and we've removed the bottom, and we cut the slit, we could take that and unroll it. Okay, we could smooth it out. And if you were to unroll that shape, what would you end up with? You would end up with a rectangle, wouldn't you? Right? Picture that in your head. You cut this side, you unroll it, and you end up with this rectangle that's flattened out in front of you. And again, this is assuming that we've removed the top and the bottom. Okay? Excellent. So, once we've unrolled it, we have a shape that's recognizable. We have a rectangle, and we definitely know how to find the area of a rectangle. So the trick here is trying to discover what is the length of this rectangle and what is the width of this rectangle based on what has been given to us here. And actually, I'm going to throw one more measurement in here. I'm going to say that this is an 8. We're going to say this shape is 8 inches tall. All right? Okay, so what would be the width of this rectangle that we've unrolled from this can? Well, it's going to be 8, right? Because this 8 is the same length as the side of our can. All right, so that hasn't changed. It's still 8. What's the length? Well, the length is kind of starting at where we cut it, right here. And it's just however long this line is, wrapping all the way around the can, right? Whatever the length of that line is, that is the length of this L, or this side. So how can we figure out the length of this line? Think about that for a second. It's actually something you've learned how to do. It's simply the circumference of this circle that makes the top, right? The distance around that circle. And we know how to find the circumference. we've learned that the circumference of a circle can be found with the formula 2 pi r, right? So we can do that. Let's do it. We have a 2 times pi times r, which is given to us. It's a 3. So we're multiplying that by 3. 2 times 3 is 6. So we end up with 6 pi as our circumference. So this length here is 6 pi. There we go. Now, all we have to do is find the area of this rectangle. And the area is simply length times width, which in this case is 6 pi times 8, which is going to give us 48 pi. Okay? And I should probably say inches squared. Excellent. So that is the area of this circular part of the can. All right? We actually give this part a name. Whenever we're trying to find the area around a three-dimensional object like this, and we're not including the top and the bottom, we call it the lateral surface area. So this right here is the lateral surface area. It's a good one to write down in your notebook because that will come up later too. Lateral surface area. Sometimes they might even ask you only to find the lateral surface area, and they won't ask you to include the top and the bottom. So it's important to know that term, lateral surface area. It's the area of the sides around the top and bottom. In this case, just the one side. All right? Excellent. So we have 48 pi for our lateral surface area. We have 9 and 9 for our top and bottom. Those are all of our sides. We're ready to add this up. So if we add this up, what do we end up with? 9 and 9, 18, 26, 66 pi inches squared. Now you could certainly multiply the 66, by the 3.14 if you wanted to, and come up with a number, and then put your inches squared. I'm just going to leave it as 66 pi inches squared. All right, so that is the surface area for a right prism. All right, now last problem here. We're going to combine what we've learned. We're going to take this rather odd-looking shape, and you'll have to pardon my drawing. It's not perfect here, but it's an odd-looking shape, which is a combination of a prism and a cylinder. All right, you can see kind of the cylinder part over on the right-hand side, and then you can see the rectangular, the prism side over on the left-hand side. All right, this down here is just simply a drawing of the base. So that is the base of the shape if we were to just flatten out the base. Okay, so how would I find the surface area for this shape? Well, how many sides do I have? I've got the top, the bottom, the two sides, and or actually the front and the back. And then you've got this side and this weird side here, this curved side. All right, so how are we going to do this? Well, it's pretty easy. Let's start by finding just the area of the base. And because these are all right angles, I will tell you that these are all right angles. We know that this base, maybe if I just kind of draw this in, would this help? Maybe. I don't know. Maybe this makes it worse. If I kind of do something like that. It's not perfect. Maybe that'll help a little bit. But we're going to be looking at this base right here. That is this shape right here. Okay? So let's find the area of that base. And to do so, we have to combine what we know about circles and rectangles. So the area of the rectangle is going to be 4 times 8, right? Which is 32. We'll just say this is inches. So we have 32 inches squared for the rectangle. But now we've got this semicircle right here. So what's the area for a circle? Well, it's pi r squared. And we've talked about this before. If it's a semicircle, what do? We cut it in half, because it's half of a circle, right? So we divide it by 2. So let's go ahead and do that. So we have pi times the r, which is a 2 squared. Maybe we'll just do that in our heads. 2 squared is going to be 4 over 2. But that can be reduced to simply 2 pi. All right? So we have 32 inches squared for the rectangular part, 2 pi for the circular part. And that combination, that sum, 32 plus 2 pi, is going to be the area of this base. Okay, in this case, because we're adding and we have pi in here, let's actually multiply that out. So let's take 3.14 and multiply it by 2 to get 6.28, and then add that to 32. 32 and 6.28 is 38.28. So we'll just write that in here. 38.28 inches squared. So that is the area of the base. Now, because this is a right solid, right, the top is going to have the same area. So we have, maybe we'll just change color here so we don't get confused. Over here we have our tally of 38.28 for the bottom, but then also another 38.28 for the top. And now we need to find the area for the sides. And this is where it gets kind of tricky. This side wouldn't be too bad. It's just like a rectangle. But this side has this weird curved edge to it, making it pretty tricky. So what are we going to do? Well, we're going to use what we know about lateral surface area. Going back to our lateral surface area. What do we know about the lateral surface area? Well, we know that, again, if we were to cut this straight up and unroll the whole thing, we could unroll it into one very, very, very large and long rectangle. Be bigger than that, I guess, even. But it'd be one really long rectangle if we slid it up the front and then unrolled the whole thing. All right? And we know that this side of the rectangle is going to be whatever this height is right here. And they didn't give us that, so I'm going to have to throw a number in there. Let's say it's a 4. Okay? So if that's a 4, then this has to be a 4. Okay? Now, this distance around this whole shape is going to be the length of this rectangle. And that's the tricky part. So how would we do that? Well, let's look at our base picture here. We know that it's 8 units long, but then we have to figure out what this curve is. And then we know that this is another 8 right here, and this is 4. So finding the distance around this shape is pretty simple up until this curved portion. So how could we find the circumference of this semicircle? Well, go back to your formula. So the circumference is equal to 2 pi r. But in this case, we only want half of it because it's a semicircle. So we're going to divide that by 2. Which actually simplifies things a bit because these 2's can cancel out, and we end up with the circumference being pi times r. And the r is a 2, so we end up with pi times 2, or 2 pi. If we multiply that out, which is exactly what we did up here, 2 times 3.14, we end up with 6.28. So that is the circumference, 6.28 inches, distance around. So the distance around this whole shape, kind of starting from here and following this all the way around the shape and back, that distance is going to be this 6.28. That means when we cut this up the middle and we unroll the whole thing, this length is going to be 6.28. You following me here? So now to find the area of this lateral surface, we multiply length times width. So we take 6.28 and we multiply it by a 4. What's that going to give us? 25.12, right? So this area is 25.12 inches squared. So that's an important one. All right, now what do we have to do? Are we done? Well, no, right? I'm going to give myself a little more real estate here. Now we found the area of all the sides. We have the top, we have the bottom, and we have the lateral surface. So now we need to add all of that up. So we're going to put that over here, 25.12. Add this whole thing up. We end up with, let's see, 18, 6, 21, and 10, if my math is right there, 101.68 inches squared. That is the amount of wrapping paper we would need to cover this whole shape. All right, so hopefully that makes sense to you. Surface area is not difficult if you have all your other formulas memorized, and if you are able to kind of be creative and remember this rule about the lateral surface area. You know, it makes it a lot easier. Rather than taking each individual side here, the lateral surface area really comes to the rescue, because you wouldn't be able to figure out, you know, the surface area of this curved portion of the shape. All right, very good. So I think we will stop it there. Good luck with your seat work, and I will see you tomorrow.